Hello, everyone. My name is Nun Lopch, and I work at Microsoft Research in Cambridge. And today I'll tell you a little bit about how computers work and how they run our programs and what is this thing called compiler. So you may have heard that CPUs run on binary code. So there's this long stream of zeros and ones that go through the CPU, and then it produces another stream of zeros and ones. And you may wonder, how do we go from the code that we write? So here's a snippet of code in C++, but you can think about, JavaScript or Pascal or any other language you have heard of, but also, micro bit make code. And how do programs written in these languages, run on the CPU? Because the CPU only wants binary code, doesn't want these English-like languages. So what's the magic that transforms these programs into binary code? But let's take a step back and have a look at what's inside our computers. So in the middle, we have the brain, which is called the CPU. And here on the slide looks pretty big, but what's actually inside is the size of your nail. It's very small. And there's all the computations, all the calculations inside the computer. Connected to the CPU, we have the RAM, which is a short-term memory. So it stores the calculations that are in progress by the CPU, so all the results of what it's doing, and short-term things that stay there for seconds to minutes or maybe a few hours, but not much more. Then we have the long-term memory. In this case, in this picture, we have an SSD disk. So this is where your files are stored, the programs, and everything that should be stored across reboots of the computer. Then we have these peripherals because we need to interact with the computer. We need to be able to see what's doing. We need to give instructions. So connected to the CPU, we have the monitor, we have a keyboard, and we have other kind of boards. For example, here in this picture is a wireless network card. And so in this slide, we see pictures of the components that go into like a desktop computer. But smartphones, for example, have all these components, but just much, much smaller. But it's exactly the same components. Another cool thing is called the motherboard. So this is where all those components that I've shown are attached. So for example, here in the center, we have this is where the RAM memory goes. So it's attached here. So this motherboard has space for 4. And then here is where the cards go. For example, the network card that we saw, or a GPU, things like this go here. Here on the left, it's where the CPU goes. So it's hidden by a fan, but it goes behind the fan. Here we have a little bit of a battery, so the motherboard can keep, for example, the clock, so that the time in your computer stays current. Then we have a load of small chips spread across to control, the data movements and so on. And so this is the size of a motherboard of a desktop computer. Your phone, again, will have the very same motherboard, just much, much, much smaller. Okay, so let's go back to our CPU. So programs are these huge, very long sequence of bits. So it's usually like millions or even billions of bits, right? And then the CPU takes this and consumes these bits at a super high speed. And then it outputs another big sequence of bits, okay? And so how does CPU knows what this thing means? So each sequence, each small sequence of bits has a very specific meaning. For example, the one in red may mean, z is equal to x plus y, and the CPU takes this and does the computation. And then after that, is that w equals to z plus 2, and so on and so forth. So this program is divided into instructions, and each instruction is just a sequence of bits. And then the output is similar, right? So for example, that output over there may mean that z is equal to 4 because the CPU did the operation, so x plus y is equal to 4. But the output is richer than that, so it can also have instructions like, draw a green line on the screen. Or you can have other things like print this document or write something to the disk and so on and so forth. So the output has a lot of different kinds of instructions. Okay, but writing programs in binary code is very tedious and very error prone, right? So we have millions of bits. So if you just flip one bit, it becomes wrong. And you can imagine if you have millions or billions of bits, it's so easy to get it wrong. So we don't really use this binary representation. So actually we use something called hexadecimal notation, and hexa means 16. And you can see in this table that the hexadecimal digit corresponds to 4 bits. So on the left, we see the decimal notation, which is what we learn in school. And up to 9, hexadecimal and decimal are exactly the same. But then, to represent numbers from 10 to 15, use the letters A, B, C, D, E, F. Okay, and this clever representation allows us to represent 4 bits with a single character. And so this compresses a lot the representation. So often when we talk about binary code, we represent in hexadecimal. So it has exactly the same meaning. So the program that is here in the bottom is exactly the same that is at the top, right? Exactly the same meaning. It's just that the first 2 lines in the binary program are represented by a single line here, because we go from 4 characters to 1. So next time when you hear about binary code, think about hexadecimal. Moreover, usually we prefix with 0x because there are more notations than just binary and hexadecimal. So we prefix with 0x to mean that it's hexadecimal. Okay, that's all it means. If you are using Windows and if you open the calculator, you actually can translate between binary and other notations. So if you click on the button on the top, you can change it to programmer mode. And then you see that it will translate to hexadecimal, the decimal, so your school numbers, octal, and binary. So you don't actually need to know how to translate it by hand, so you can use the calculator. Octal notation, as the name implies, is so each digit represents as 8 possibilities, so it's from 0 to 7, and it's a different notation that is also widely used, and it represents 3 bits. So 0 to 7 can represent 3 bits. Okay, so you can use your calculator to convert between these different notations. Okay, so now the question is, how do we go from this program, which is like English-like, to binary code? And the answer is, it's a compiler. So there's this thing called compiler, which is often represented by a dragon. And why do we call it a dragon? So this is just a curiosity. The reference book for compilers, which was published roughly 35 years ago, had a dragon on the cover. And so the book was then known by the Dragon book. And the Dragon represented the complexity of writing a compiler, because compilers are really complicated programs. And so the Dragon was this complexity, and the Knight was a compiler developer armed with all these tools that tame the complexity. So, and if you look, the Knight as some words, for example, here we see like data flow analysis. Here we see ALA, parser generator, and these are techniques that are used to build compilers. So this is and from this Dragon book, you know, and since then compilers are now known, as Dragons. Okay, so how do these Dragons work? So let me give you a quick overview. So we take the program, and then the compiler builds what's called the abstract syntax tree. So this is nothing more than these circles and lines, which are called vertices and edges. So this is called a graph. And this is a one-to-one, roughly, translation between the program and this tree representation. Okay. And then we go from here to an intermediate representation. And this representation is much closer to what to the instructions that the CPU can execute. Much lower than what AST is. And then from this intermediate representation, we can go to the binary code, and then which can then be executed by our very happy CPU, because now it has binary code. Okay, so let's zoom in each of the phases. So the first phase is called parsing. So we take this text, right? And text is usually not very good for computers. We like a more structured representation of the data, which is what this AST gives us. So the compiler takes this text, does the thing called parsing, and identifies, for example, if there are mistakes in the program, right? So here we may have forgotten to put a semicolon, or may not have something wrong in the syntax. So this during parsing will generate warnings and errors, and try to help the developer as much as possible so they can fix their code. And then we create and if it's all fine, we create this tree or graph where each node, so each circle or vertex, will have, like for example, this bit here is going to be one circle, this will another circle, and then finally the whole thing will be yet another circle, and all connected with these errors. Okay, so this representation, helps us because it's structured, but it's still very much close, very close to the code that the developer wrote. Second, we go from this AST to this intermediate representation. So intermediate representation is much closer to what the CPU executes. So the instructions are close to what CPU does. So so this transformation is a bit more complicated because we need to transform what's in the program into instructions that CPUs kind of like. But this step is a bit more complicated. Then a super important thing is optimization, right? So we all want programs to run fast, as fast as possible, like instantaneously, if possible. We want to reduce code size because we don't want to wait forever for the app to download, right? Also, we wanted to reduce power consumption because we want our phones to last, the battery to last longer, and we want to reduce memory consumption because memory is finite, memory is expensive. So this is the role of the optimization step. So we try to rewrite the intermediate representation in many ways until we come up with a smaller, better, faster program that does exactly the same thing but executes faster on the CPU. And finally, we take this intermediate representation and we want to generate a binary code. And the complexity here is that different CPUs have different instructions. For example, phones usually have ARM CPUs. By the way, ARM CPUs are developed here in Cambridge. But desktop computers usually have like Intel or AMD CPUs. And the CPUs are very different. They have different instructions. So the binary code we need to produce is completely different. So the compiler needs to know to which CPU it's generating code to and adapt and optimize the code differently for that particular CPU. So this phase of the compiler takes care of that. Okay, so let's sum up again. So this is the summary. So we go from program to abstract syntax tree, to intermediate representation, then to binary code, and then finally, our happy CPU can execute our program. So in a nutshell, this is how our compilers or our dragons work. And so probably I've never heard about compilers before, but they are everywhere. You just don't know that they are there. So where can we find them? For example, in browsers that you use to access the internet, they have compilers inside. You may have heard about JavaScript. So JavaScript is a language that is used by websites to implement their functionality. And of course, this language must also be compiled. So every time you go to a website, you have a compiler hidden in the browser doing all this compilation for you to make internet faster and safer, etc. We also find compilers inside games. For example, DirectX and OpenGL, these are the main graphics frameworks, so they take care of all the graphics in the games, and they too have compilers to accelerate the rendering of graphics for games, for example. And again, so every time you play a game, you are using a compiler and you don't even know. Then we have compilers and code editors, of course. So these are the programs that developers use to write code. And so we need to compile the code before we ship it to users. And so all code editors will have a compiler. Here is just two examples of major code editors. And educational tools also have compilers. So the Scratch and these microbit make code, for example, they allow you to write programs with these blocks. I mean, it's not how we usually code because we usually have these kind of English-like languages, not blocks, but you still need to go from these blocks to binary code. So these tools do have compilers inside as well. So to wrap up, what we have seen today, so we have looked a bit in what's inside the computer. We realized that CPUs run on binary code, so they take programs written as a sequence of bits and they output also a sequence of bits. And we looked a bit as this dragon, so how compilers work, how they go from a program until the binary code that can be executed on a CPU. So this concludes the talk today. I hope you have enjoyed and you learned a little bit more about computers. If you have any question, feel free to send me an email. As a bonus question, think about it. Who compiled the compiler? And also, who compiled the first compiler if there was no compiler before?